This screencast is on limiting reactants in stoichiometry problems. Now, in our last video on stoichiometry, we talked about s'more making and how the reaction, if you will, for a perfect s'more was 2 graham crackers, 3 chocolate pieces, a roasted marshmallow to make a perfect s'more. And that if we wanted to write that as a chemical reaction, we'd have 2 of the graham cracker squares, 3 of CH for chocolate pieces, 1 M for marshmallow, and then that made 1 G2 CH3M could be the formula of the s'more. And so I wonder if you've ever been to a bonfire and maybe someone showed up with a box of graham crackers and someone with a package of chocolate and someone with a bag of marshmallows. Do you know what will run out first? Well, limiting reactants is the idea of calculating that. What reactant or what food ingredient here is going to run out first when we try to make s'mores? To figure that out, we need to calculate just how many s'mores, just how many G2CH3Ms can we make from each of our reactants. We do 3 separate calculations. So let's start with the graham crackers. They come in sheets like this, and I have a box at home. The box says it's got 13 servings, and it also says that a serving is 2 of these sheets. Now, each of these sheets has 2 G's on it, but again, it says that a serving is equal to 2 of these full sheets. Okay, so that's some quantities that I'll need in my first problem. So I start with what I know I have. My known is that I've got 1 box of graham crackers. I'm going to put that known over 1 just so I don't accidentally put anything else in that denominator. I'm going to do unit conversions. I'm going to bring down my unit box. Well, what do I know about a box of graham crackers? The only thing I know about that box is that it has 13 of those servings. Well, what do we know about serving? Bring down servings. I know that every 1 serving has 2 sheets. Well, get rid of sheets. I'm trying to get all the way to s'mores, to G2CH3M. Well, I know that every 1 sheet has 2 G's. Oh, now I'm getting somewhere because if I bring down G, I know how many G's are in a s'more. For every s'more, there are 2 G's in 1 s'more. I need 2 of the graham cracker squares to make every 1 s'more. And so I've gotten rid of the units box, the servings, sheets, and G to get to my s'more, or how many of the product I can make. These 2's actually cancel, and so then we just are left with 13 times 2 is 26 s'mores can be made from the graham crackers. So then I go to the chocolate bars. I need to repeat this process for the chocolate. And there are 6 full-size chocolate bars in the package, and each one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 CHs in 1 bar. So there are 12 of those chocolate pieces in each bar. So what do I know? What am I starting with? Well, I know that someone brought 1 package of chocolate to the bonfire. I know something about the packages. Oh yes, that there are in every 1 package 6 bars of chocolate. And then what do I know about the chocolate bars? That they contain 12 CHs in every 1 bar. And I know from CHs how to make my s'mores. I know that 1 s'more needs 3 of those chocolate pieces. And so then I'm going to be able to make 24 G2CH3 or s'mores from the chocolate. All right, and last is my marshmallows. My marshmallow bag says that there are 12 servings in the bag. I have a bag of marshmallows at home. It also says that a serving is 4 pieces, so 4 marshmallows. Now I know someone brought one bag. What do I know about the bag? That it contains 12 servings in every bag. What do I know about a serving? Well, every one serving is 4 marshmallows. And I know how many marshmallows are in my s'more. A s'more just needs 1 marshmallow. So bags cancel and servings and marshmallows. And wow, from the marshmallows, I can make 48 of the s'mores. Now, in a limiting reactant problem, we can only make as much s'more as the limiting reactant allows us to make. So the point is, when we're analyzing this, we ask ourselves, can we make 26 s'mores? Can we make 24 s'mores? Can we make 48 s'mores? Well, we can only make 24 s'mores because at that point, once we made the 24th s'more, we are out of chocolate. And so the way I like to make s'mores, you usually run out of chocolate first. So we'd say that all we can make are 24 s'mores, and that the limiting reactant then is the chocolate. It's the one that will run out first. So the limiting reactant is chocolate, and it's going to limit us to only being able to make 24 s'mores. We'll never be able to make the 26 or the 48 s'mores. So in limiting reactant problems, we're going to pick the least amount of product, and that's how much product we'll be able to make. So just to review, what's a limiting reactant? The reactant that runs out. It's going to cause the reaction to stop. And so in our example, the chocolate was limiting. Once it runs out, we have to stop making s'mores. Graham crackers and marshmallows were both present in excess. Once even one reactant runs out, the reaction stops because it can't make any more of the product. So let's look at some chemistry examples. Now, in our examples, we're always going to do as many stoichiometry problems as we have reactants with given known quantities that could potentially be limiting us. Now, if it says something is present in excess, that's not limiting us, so we don't have to worry about that at all. But we'll do a stoichiometry problem for each known that could be limiting us, that we're given a value for. So this problem says how many moles of water is produced when 2.3 moles of O2, there's one known, and 2.3 moles of H2 react. So we have two known given values. 2.3 moles O2 is one known. The other known is 2.3 moles of H2. Now it says how many moles of water is produced. This is just a mole to mole problem. How do we get from moles of one compound to moles of another? Well, we need the balanced equation. So the way that we're going to get there is we're going to use the coefficients from the balanced equation. So in the first problem, let's bring down moles of O2, and we want to get to moles of water. So we look for the coefficient. 2 moles of water are produced when that's an implied 1 mole of O2 reacts. And so we just get 4.6 moles of water are produced from the oxygen. Now we're going to do the same thing for hydrogen. Bring down moles of hydrogen. We want to know how many moles of water can be produced. We know it's for hydrogen, it's 2 to 2. Okay, well those 2's actually just cancel, and so 2.3 moles of water can be produced from the hydrogen. Now here's the thing with stoichiometry problems, we can only make the lesser amount with our limiting reactant problems. We can only ever make the 2.3 moles of water. At that point, we will run out of hydrogen. So hydrogen is our limiting reactant. So hydrogen is our limiting reactant. It allows us to only be able to produce 2.3 moles of water. Sometimes folks mistakenly add up these two values, or they subtract them, or they do some calculation. But all we're doing is picking the smaller one and ignoring any larger values. We can only make the lesser amount in a limiting problem. So we're going to try another type of limiting reactant problem. It says if you react 10.5 grams of NaOH and 7.5 grams of barium chloride, how many grams of NaCl, sodium chloride, is produced? So again, we have two knowns. We have 10.5 grams of sodium hydroxide is one known. We'll put that over 1. Our other known is 7.5 grams of barium chloride. Put that known over 1. Now we're doing a gram to gram problem here because we want to get to grams of sodium chloride. So we're getting to the same end point with both of our problems. So in order to get rid of grams of NaOH, we're going to have to get to moles of NaOH. We're going to have to go from grams to moles using molar mass. So let's calculate that down here. We'll need a sodium and an oxygen and a hydrogen. And we're going to add up the masses of sodium and oxygen and hydrogen. And then we'll put that with grams because that's the number of grams that are in every one. It goes with mole. Now, we'll bring down moles of NaOH because here's where we can switch compounds, mole to mole. We can switch from sodium hydroxide to, we're trying to get to the compound sodium chloride. So trying to switch to sodium chloride, we can do that at the mole to mole conversion point. We'll look at their coefficients in the balanced equation. We've got a 2 for sodium chloride and we've got a 2 for sodium hydroxide. Now we still need to get to grams of sodium chloride. So we'll get rid of moles of sodium chloride and the last conversion is to grams of sodium chloride. And so we'll need the molar mass of sodium chloride. So we'll add up a sodium and a chlorine and get 58.443 grams are in every 1 mole. Let's put this too. So we'll put the 58.443 with the grams are in every 1 mole. And we'll go ahead and calculate this and we should get 11 grams of sodium chloride. Now we need to do the same process for barium chloride. We need to bring down grams of barium chloride and get to moles of barium chloride. So we'll get its molar mass. There's only 1 barium here. But for chlorine, there's 2 chlorines. 137. That should be a 137.327. .233 grams per mole. So our 208 is going to go with grams because that's the number of grams that are in every 1 mole. Now bring down moles of barium chloride and we can switch compounds. Now that we're in moles, we can use the coefficients from the balanced equation to switch to the desired compound, sodium chloride. Again, there's that 2 in front of sodium chloride, but an implied 1 in front of barium chloride. Now, it doesn't ask us to be in moles of NaCl when we're done, though. It asks us to be in grams of NaCl. This last step is usually the same when we're dealing with the limiting reactant problem. We're trying to get into grams of the product, sodium chloride. So we can just copy down that molar mass of sodium chloride. When you multiply everything in the numerator, divide by what's in the denominator, the 208, you should get 5.9 grams of sodium chloride. Now think for a second about how much sodium chloride you think can be made. It's only the lesser amount. You can't add these up. You can't subtract the two masses. We can only make 5.9 grams of sodium chloride. We'll never make that full 11 grams. And then the question is, well, what is the limiting reactant? Well, then it's the reactant that produces the lesser amount. And that reactant was the barium chloride. So barium chloride is the limiting reactant. And it limits us to only being able to make 5.9 grams of sodium chloride. And so that would be sort of the final results of this problem. And so now hopefully you've seen a couple of different ways that you could be asked to calculate limiting reactants. You could be asked to calculate them, for example, in a mole-to-mole problem or a gram-to-gram problem.